Good evening, buenas noches, everybody. Welcome to day one on week 16 of the semester. We pretty much only have this week and next week of material in order for us to end the semester. So at this time, we are going to continue talking about the topics of chapter 9. Specifically, we are going to focus now on the topic of buffers, okay? So let's first define what is a buffer. A buffer is going to be a solution that is going to resist changes in pH from when you add acids or when you add bases. Buffer solutions are very important. And in our body, we even have at least 4 known types of buffers that are going to regulate the pH in the body. Now, why is it that they're important in the body? Well, the buffers in the body are going to absorb either the hydronium or the hydroxide ions that we may obtain from foods or even cellular processes that are going to be occurring in the cell. All of that is going to, again, make sure that we maintain the proper pH. To give you guys an example, the blood that is running through our body has a specific pH, which is 7.4. And that blood needs to be maintained at that pH of 7.4 in order for many of the biochemical reactions that happen in the body to occur properly. Now, overall, if we look at a buffer solution, and here we have some illustrations just showing how a buffer works, understand that if you have just pure water, as you can see in this illustration, pure water has a pH of 7.0. So if you add acid to a solution of water, what's going to happen is that then the pH of the solution is going to drop drastically. If again, you start with a solution of just water, but instead of adding acid, you add base, the pH of the solution will also change drastically, as you can see, to a basic pH. Now, what if instead of having just pure water, we have a buffer solution? Well, in the case of a buffer solution, the chemicals that are present that will create that buffer solution, it doesn't matter if you add acid or if you add base, the buffer solution is going to permit that the pH is going to be retained very close to the initial pH of the solution, okay? So let's first now establish what makes a proper buffer solution. So in order to know what is a buffer solution, we need to remind ourselves of what is a strong acid or a weak acid. The majority of the buffers that are out there, understand that they are produced by a combination of a weak acid. So this is why it's important that you guys know your acids. And that weak acid is going to be paired with the salt of its conjugate base. Okay, so to give you guys an example of a buffer, here we have the following pair. The molecule that we have on the left, this is acetic acid. How do we know it is a weak acid? Because remember that I mentioned to you that, and even for the last exam, you guys needed to memorize which ones are the 6 strong acids. Once you know the 6 strong acids, anything outside of those 6 is a weak acid. Acetic acid is not a strong acid because it's not part of those the strong acid list. Remember that your strong acids are going to be hydroiodic acid, hydrobromic acid, hydrochloric acid, nitric acid, sulfuric acid, and perchloric acid. Those are your 6 strong acids. Any acid other than those 6 is always going to be considered weak. Now, the conjugate base of acetic acid is when acetic acid loses a hydrogen. And when acetic acid loses a hydrogen, then it's going to have the following chemical formula, C2H3O2. And this is acetate. Now, in order to make this a salt, all we have to do, guys, is that we need to pair it with an element from group 1A in the periodic table. So sodium, lithium, potassium, rubidium, okay? So as long as you have that conjugate base of the weak acid, the reason or the way that we make it a salt is specifically by pairing that conjugate base with an element from group 1A from the periodic table. So taking that into consideration, let's actually look at different pairs of compounds and determine if they're going to be making a buffer solution or not. And we have the following pairs. Letter A, we have sodium hydroxide and we have sodium chloride, okay? From our knowledge of acids and bases, we need to identify that, remember that for a buffer system, what we're looking for is a weak acid paired with the salt of its conjugate base. So if we look at the first pair, sodium hydroxide, this is a strong base. Sodium chloride, this is a salt. Now, based on the definition of a buffer, is this going to form a buffer or is this pairing not a buffer? What do you guys think? Let's put it in the chat. Is this a buffer or it is not a buffer? Great job, Katie. I agree with you. Thank you, Maria. I agree with you. Thank you, Vanessa and Dominique. I agree with you guys. This is not a buffer. First of all, where is our acid? We don't even have a weak acid. And just because we have a salt, that doesn't mean that we can have a buffer. Let's look at the second pair. In the second pair, we have carbonic acid. And then we have sodium hydrogen carbonate. So if we go back into our knowledge of acids and bases, if we have H2CO3, the conjugate base of it is when we take one hydrogen out. So this is going to become HCO3 -1. Then, in order for us to have the salt of the conjugate base, we're going to pair this HCO3 with, again, one of those elements from group 1A. So the thing that remains here is, well, this is the salt of the conjugate base. I agree with that. Now, we need to find out, is carbonic acid a weak or strong acid? What do you guys think? Carbonic acid, is that strong or weak? Great. Since this is a weak acid, and we know that that NaHCO3 is the salt of the conjugate base. Is this a buffer or not? Exactly, this is a buffer. So let me put here, not a buffer. This is a buffer system. Let's look at the third pairing. Remember, your acids can be binary acids, they can be oxy acids. The main thing is, are they strong or are they weak? HF, what kind of acid is that? HF, strong or weak? Awesome, great job in the chat. This is a weak acid. So if HF is acting as an acid, remember, when we do the conjugate base of it, the conjugate base of HF is F-1. So KF is going to be the salt of the conjugate base, because remember, the salt is formed from the conjugate base paired with anybody from group 1A. So what do you guys think? HF and KF, is that a buffer or not a buffer? I agree with Katie. I agree with Maria. So HF and KF, that is a buffer. Take a minute, look at the chemical formula of the two molecules in the last pairing, and let's determine if they will form a buffer or not. So again, I'm going to give you guys a minute. Determine if the pair on letter D is going to form a buffer or not. What do you guys think? KCl and NaCl. Is that a buffer or not? I see 2 no's. There are 9 students here. What do we think? We see a yes. We continue to see no's. We continue to see no's. The correct answer is no. Why is the correct answer that KCl and NaCl are not a buffer? Let me just write it here. This is not a buffer. Again, KCl and NaCl, none of them are acids. Both KCl and NaCl are actually salts. So this is a salt and this is a salt. And in order to have a buffer, you always need, always, you guys, a weak acid paired with the salt of its conjugate base, not any conjugate base, its conjugate base. Okay? So understand that the definition of a buffer is specifically a weak acid paired with the salt of its conjugate base. Any questions trying to determine if a pair of molecules is a buffer or not? Make sure that you know for the final how to identify if a particular molecule is a strong acid or a weak acid, and also review the concept for how to determine the conjugate base if you have an acid. Give me one moment. Now, let's actually learn how, at the chemical level, a buffer actually works. Okay? So, as you can see, buffers work because the weak acid in a buffer is going to neutralize the bases that are added to our buffer system. And for example, if instead of a base, you add to your buffer system an acid, then it is the role of the conjugate base or the salt of the conjugate base to neutralize that specifically incoming acid. Let's look at a particular example so we can see these reactions at work. So here we have a particular buffer system. So this is our buffer. In our buffer, our weak acid is acetic acid. Our salt of conjugate base is acetate. The only thing that you don't see here is the sodium, the lithium, or the potassium. So let's just write it in. Let's just put in the sodium here. Okay. Let's first go over how does a buffer system resist changes when we add specifically acid. So this is if we add acid to the system. So as you can see in the first bullet point, adding H3O plus or any acid for that matter to the buffer means that that added acid is going to react specifically with the salt of the conjugate base for my weak acid. So if this is my buffer system and then I add acid to my solution, what happens overall is that in this process, the acid reacts with the salt of the conjugate base. So in this case, it's going to be C2H3O2 -1. And when acid reacts with the conjugate base, what's going to happen is that in turn is going to make HC2H3O2. So when we compare these bar graphs, we can see that when we add acid, that acid reacts with the salt of the conjugate base, and the product of the reaction is more weak acid. So when we look at the bar graph, then it makes sense how the bar graph for the acetic acid upon addition of the acid is going to be larger than the one of the conjugate base. Because remember that the conjugate base is going to be reduced in concentration just because it has reacted with the incoming acid to make more of the weak acid in our buffer system, okay? Now, what happens to a solution that instead of adding acid, we are going to add base? So this part of the equation, as you can see in the bottom, it says adding OH minus or adding base, what it does is that it neutralizes the weak acid. Let me illustrate that. So let's say that we start with the following buffer system. When we add base to the system, understand that what happens is that the base is a reactant, and that base is going to react with the weak acid in our buffer. So in the case of the example that we have is that it's going to react with HC2H3O2, and the product of that reaction is going to be that the weak acid acts as an acid and it gives the base a hydrogen. So the product of this reaction is that we're going to make C2H3O2 -1. So that's why we see in the right side of the arrow that now our concentration for the C2H3O2- is larger compared to the weak acid. And that's because the weak acid is getting used up by the incoming base in order to resist those changes of pH. So as you can see, overall, what's going to happen is that there's going to be acid-base reactions, okay, that are going to neutralize the incoming acid or the incoming base in order to resist these changes of pH. And that's basically how a buffer works, okay? Now, I mentioned to you guys a few moments ago that when it comes to our blood needs to have a pH of around 7.4 in order to have proper functioning of the cells, okay? So in our blood, we actually have a buffer system, which is known as the blood buffer system. This blood buffer system consists of the weak acid, carbonic acid, and then the salt of its conjugate base, as you can see, is going to be HCO3. We don't see the sodium, potassium, or lithium, but this is going to be the conjugate base of the system. Now, understand that the equilibrium for this buffer system can actually be affected by respiration. Because through the process of respiration, as we intake or as we exhale, we can actually have more CO2 being retained in the body, or we can release too much CO2. So understand that there's certain medical conditions that will affect this blood buffer system. Those medical conditions are known as respiratory alkalosis, which is what we have on the left, and then we have respiratory acidosis. So when it comes to these, let's actually explore these two respiratory conditions and understand how changes in the levels of CO2 in the body actually result in changes of pH by incorporating the use of buffers, the concept of pH, the concept of chemical reactions, okay, overall in this process. Let's first deal with respiratory alkalosis. As you can see, respiratory alkalosis is actually caused by hyperventilation, which can happen because of anxiety, because of fear, or at times it could be mechanical ventilation that creates this process. Now, understand that under respiratory alkalosis, seizures, lethargy and confusion can happen, lightheadedness, tachycardia, all kinds of conditions. Now, let's now understand why is it that we call it respiratory alkalosis. So, as you can see in the lungs of the figure, overall, the CO2 in the body is going to reduce. So the CO2 in the body is going to reduce. Now, if the CO2 in the body reduce because the reaction to be creating the buffers that are part of this system are controlled by the process of Le Chatelier's principle, well, if there's a reduction in the reactant, we need to remind ourselves what's going to happen to the rate of the reactions that are going to be modified in order to get the system in equilibrium again. So, taking that into consideration, let me just remind you guys of this work that we did last time. And let me just put the information back here. Give me a few moments. Let me make adjustments here so we see the table. Because as you can see, all of these topics build on each other. Okay, so when we have respiratory alkalosis and we reduce CO2, what are we doing to the system? Are we adding reactant, removing reactant, adding product, or removing product? Which letter? A through D. Which letter is happening when we are lowering CO2? Thank you guys, exactly. We are removing reactant. So if we're removing reactant, in order to regain equilibrium, overall what's going to happen is that, as you can see, the shift of the reaction is going to be towards the reactant. What does that mean? That these two components are going to come together and create more carbonic acid. And in turn, that carbonic acid is going to be creating more CO2 and water in order to replenish that CO2 that was lost. Now, because you can see here that we are combining H plus and HCO3 minus, that means that overall, in respiratory alkalosis, there is a decrease in H plus concentration. And whenever we have a reduction in H plus concentration, it results in an increase of pH. So that's why this is called respiratory alkalosis. As you can see in the figure, the pH is going to go up higher than 7.45, which is the higher end of the pH, because it's between 7.35 to 7.45. So that means that the pH of the blood is going to go higher than 7.45, okay? Now, what happens if instead of having respiratory alkalosis, we have a condition that results in respiratory acidosis? Understand that I'm going to be erasing these notes, but this is just a copy of the slide that we were talking about. So don't be afraid that all of a sudden the notes are going to be gone. There will be on the class website. It's just that I need to erase the notes that we did here so we can talk about respiratory acidosis. Let me just erase this. So then we can talk about acidosis. In respiratory acidosis, as you can see, some of the causes for respiratory acidosis includes respiratory depression, and that can happen because of anesthesia, because of an overdose, okay? It can happen because there's an airway obstruction, okay? And then there's other conditions like pneumonia. Now, what does that mean? That overall, if a person cannot breathe well and you increase the amount of CO2, that's going to result in respiratory acidosis. That process, as you can see, is called hypoventilation, okay? And hypoventilation can lead to hypoxia, okay? So, understand that some of the results of having this are skin and mucosa that is pale. Understand that it also can lead to drowsiness, dizziness, muscle weakness, okay? And there's other things described here in the figure. Let's focus now on why is it called respiratory acidosis. So in respiratory acidosis, because we cannot exhale for one of the conditions that I was mentioning, means that we are going to retain the amount of CO2 that we have in there. So we're not going to be able to reduce it. It's going to be retained and it's going to increase. So this is going to affect the buffer system, but if it affects the buffer system, it can also affect the pH. So because all of this is an equilibrium reaction, as I just mentioned to you, the Le Chatelier's principle is going to actually explain what happens overall. So if we increase the amount of CO2, what situation is happening to the system? A, B, C, or D, meaning adding reactant, removing reactant, adding product, or removing product. Great job, you guys. I like that you put A right away. So as you can see, if we are adding reactant, then the shift of the reaction is going to be towards the products. What does that mean? If we have more CO2, in order to alleviate and try to keep the system in equilibrium to the best of our abilities, what is going to happen overall is that now on increased CO2, that means that the rate of the reaction in the forward direction is going to lead overall to an increase in H plus. So let me just write it as notes. In respiratory acidosis, there is an increase in the concentration let me rewrite this word. Of CO2, and in turn, there is an increase in the concentration of H plus. If we have higher H plus concentration, that means that the pH is going to lower. And since our pH is going to be lower, okay, then that 73.5, that's why the system is called acidosis, okay? So for those of you that are going into the medical field, understand that sometimes you may see patients that have the following conditions. Any questions about buffers, the Le Chatelier's principle, or the blood buffer system for the human body? Great. Since there are no questions at this time, we are going to move on to the next chapter, which is chapter 10. And in chapter 10, we are going to be learning about proteins, which are known the workers of the cell. Okay? So let's first mention that proteins are going to be specifically biomolecules that are made of amino acids. And in section 10.1, we have a discussion of what is an amino acid, okay? So amino acids, give me a moment. Are the building blocks of proteins, okay? How many amino acids we have out there? We have 20 amino acids. There's actually more than 20, but the other 3 extra amino acids, they are not common in all cells. That's why we only talk about the main 20, which are present in all the proteins for cells, okay? So where does the word amino acid come from? As you can see here, amino acid, or the word amino acid, comes from the functional group that these molecules have. So the word amino comes from the amine that we have in the amino acid, and then it actually shows up as an ammonium group because the amine is going to collect a hydrogen. Where does the term acid come from? Well, the term acid comes from a carboxylic acid. In this carboxylic acid, under the pH conditions for the blood, we see that specifically the oxygen in the carboxylic acid loses a hydrogen. In addition to that, every single one of the amino acids is going to have an alpha carbon, and they're going to have an R group. R group is specifically a side chain. That's what we call it. And understand that this side chain is what makes each amino acid different from one another. Okay? So, you can see here the structure of the 20 amino acids. These amino acids can be classified depending on the R group that they have in their structure. Now we're going to take a closer look at the R groups for each of the following 20 amino acids. Let's start with the amino acids that have an R group that is a non-polar chain. So non-polar side chain amino acids are also known as hydrophobic amino acids. Why hydrophobic? Well, since their side chain is non-polar, and we know that water is polar because they have opposite polarities, those amino acids do not want to interact with water. That's why we call them hydrophobic. Okay? So when we look closely at the functional groups for these amino acids, we are going to notice that the majority of them have hydrocarbons in their side chains. Look, hydrogen for glycine, carbon and hydrogen for alanine, carbon and hydrogen for valine, carbon and hydrogen for leucine, carbon and hydrogen for isoleucine. Look at proline, look at tryptophan, look at phenylalanine. The majority of them have, as you can see, hydrocarbons. There's only one functional group here that we haven't explored, and that's because it's not relevant in organic chemistry, but it is relevant in biochemistry. And that is this one. This functional group is actually called a thioether. You may remember that ethers are actually built from two carbon chains that are connected by a single bond oxygen. So instead of having an oxygen, a thioether is going to have a sulfur. Remember that oxygen and sulfur live on the same group in the periodic table. So again, these are going to be the amino acids that are considered nonpolar, or in other words, hydrophobic. Then here in pink, we have the amino acids that are considered polar side chains. So if the nonpolar are hydrophobic, then the amino acids with a polar side chain are going to be hydrophilic. Okay? And when it comes to the functional groups that we see here, we can notice that we have alcohols, we have thiols, and lastly, we have amide in the side chains. Again, the side chain is going to be anything that is highlighted, and here we have it highlighted in pink. There's two more families of side chains that we have in amino acids, and those are acidic amino acids versus basic amino acids. In the acidic amino acids, the side chains, meaning the highlighted area, are going to have carboxylic acids. So what do carboxylic acids do? Okay, or I should say, the carboxylic acids, as you can see, are a C double bond O with an OH. You're not going to see the hydrogen here because this is showing the ionized form of it. But if you have a hydrogen here, that's where the carboxylic acid is. Okay. When it comes to the basic amino acid, in the basic amino acids, the functional group that we're going to see is an amine. We can see a primary amine here because the nitrogen only has one carbon chain. And we have here a cyclic system with nitrogens. This is what we called in organic chemistry a heterocyclic amine. In the amino acid arginine, it has a functional group that, again, is present in biochemistry, not in a lot of organic molecules. So having this NH connected to carbon, connected to an NH2, connected to another NH2, that is known as a guanidinium group. And that's also part of the basic amino acids, okay? So now that we know the building blocks of proteins and we know how to classify them based on the side chains, let's actually now look specifically of how amino acids come together to make a protein. So in section 10.2 is where we explore protein formation. So when amino acids come together to make a protein, they do the following reaction. Here we have two amino acids. On the left, we have glycine. On the right, we have alanine, okay? Now, understand that these two amino acids are going to come together and via a condensation reaction. Remember condensation reactions. This is a type of organic molecule. In this condensation reaction, which is actually called amidation, we are going to be unifying the carboxylate. So the chemistries are going to happen specifically here. The carboxylate of the first amino acid with the amino of the neighboring amino acid that we're trying to form a bond with. What happens overall in this condensation reaction? Well, the carboxylate loses its oxygen. The amino group on the next amino acid is going to lose one H and another H. So whenever we have two H's combining with oxygen, we form water. Then what happens overall is that this nitrogen and hydrogen that we have here are going to connect to the carbon in the carbonyl. And when that happens, notice that this, what is shown in a box, which is called a peptide bond, is nothing other than an amide bond. And that's how you link together two amino acids via a peptide bond and, or in other words, an amide bond. Now, once these amino acids, we have linked together at least 50 amino acids, that's when we consider that we have a protein. In addition, these 50 amino acids need to have a biological function, okay? So 50 amino acids, biological function, then we know that we have a protein. When it comes to proteins, protein actually have a three-dimensional structure. And in section 10.3, we are going to explore the three-dimensional structure for proteins, okay? Starting with the primary structure of proteins. So this is how protein structure is organized. We have a primary structure, we have a secondary structure, we have a tertiary structure. Now, understand that there are very few proteins that go all the way to quaternary structure. So most proteins have all three. This is only for special examples. Not everybody have a quaternary structure. Let's now define what is a primary structure versus secondary structure versus tertiary structure versus quaternary structure. So the primary structure of a protein is going to be the sequence of amino acids that are present in that protein. To actually show you guys an example, here we have the following peptide. The reason why I'm calling this peptide is because I'm only showing you a few segments, and there's only there's less than 50 amino acids. So anything less than 50 and it doesn't have a biological function, we call it a peptide, okay? So we have the following peptide. So if I'm given a peptide and I know the structure of the side chains and I know the overall structure of a particular peptide, let's understand that we can derive what are the amino acids that are present, and that's what is going to give us the primary structure of a protein. So we have the following structure. Let's understand that one of the key skills that you guys need to develop here is to understand the pattern that a particular peptide has. Once you understand the pattern, you can actually find the alpha carbons, and those alpha carbons are what are going to have specifically the side chains that we're interested in. So when we have a peptide, most peptides start with an NH3, okay? Then, right after the NH3, we're going to have an alpha carbon. Notice that after that, we have an amide bond. After the amide bond, we have an alpha carbon. Then we have an amide bond. Then we have an alpha carbon. Then we have an amide bond. Then we have an alpha carbon. Because after my alpha carbon, there's a C double bond O. O minus, I am done with my peptide. Now I'm going to look closely at the alpha carbons, and I'm going to identify the side chains that are there. So these side chains, which you can see the 3-letter codes for the amino acids here, is because I'm comparing the side chains to the highlighted portions of the molecules that we have here. That's how I define the amino acids. Looking at the side chains and comparing it to this table. So if my alpha carbon has a CH3, that means that specifically the first amino acid is an alone. In other words, an alanine. For the next one, we have CH2, CH3, and that is leucine, LEU. Then we have CH2SH. That side chain belongs to cysteine. And lastly, CH2, CH2S, CH3. That's going to be methionine. Okay? So I want to advise you guys that whenever it comes to these problems in the chapter 10 homework, understand that it is good that you have a particular table in which your amino acids are given to you in skeletal structure, because it's going to help you better with the structures that I actually utilize in the exam. So as you can see, this is just an image with specifically the names of the amino acids and their structural formulas, but is only in skeletal form. Let's actually practice how to define the amino acids that are in a particular peptide, utilizing the illustrations that mostly we're going to see in our examination and the last chapter quiz. This is how they look like, and this is going to be based on the computer program that I use for drawing these. As you can see, the instructions say, determine the one letter code for the amino acids present in the following peptides, okay? And I'm going to do the first one with you guys. As I mentioned, most peptides are going to start with an NH3. You may be wondering, but Dr. Luz, I don't see an NH3 here. Look, NH2 plus hydrogen, that means NH3. So immediately after the NH3, we have an alpha carbon. Then we have an amide, alpha carbon, amide, alpha carbon. And as you can see, after that last alpha carbon, because I have a C double bond O, O minus, that's the end of my peptide. So when it comes to this, we can see that this peptide actually has 3 amino acids in it, okay? So let's actually define, and so I'm going to go back and forth so you guys see this. What are the amino acids present in this peptide? So as you can see, the first one is where we have a CH2 bonded to OH. So when I go to this figure and I look around and you're like, a CH2 bonded to OH. Oh, found it right here. CH2 bonded to OH. That means that my first amino acid is serine. So I asked for the one letter code for serine. So specifically, if you go to this table, you can actually say, oh, serine has the one letter code S to symbolize it. So for my example, that amino acid that is in orange is an S. Let's look at the next amino acid. CH2, CH2, C double bond O, O negative. Okay? So I go here and I'm like, okay. So overall, I need a CH2, CH2, and then I need a carboxylic acid. Oh, right here. CH2, CH2, C double bond O, OH. So my second amino acid is going to be glutamic acid. Okay? When I look here, Glutamic acid has the one-letter code E. So then the next amino acid is the letter E. Last one, I have a CH bonded to a CH3, bonded to an OH. Okay? So, if I go here, and I'm trying to look around and be like, okay, I'm looking for something that is a CH, okay, that has a CH3 and an OH. Oh, right here. CH bonded to OH, bonded to CH3. So that means that my next amino acid is threonine. Threonine specifically is going to have the T as its one-letter code. So the last amino acid is T for threonine. Okay? And that's how you determine the one-letter codes for amino acids. There's one more incentive that I like to give you guys when it comes to peptides. Peptides in the chapter 10 chapter quiz, when you guys see it, are going to spell words. Looking at peptides and defining words is one of my favorite things. Like, students find it at least motivating because they know it's like, okay, I'm going to spell a word. Let the peptide guide you, okay, through the whole process. Let's take a moment and at least do this one before I let you guys go. Okay, so at this moment, let's identify that there is 1 alpha carbon, 2 alpha carbon, 3 alpha carbon, 4 alpha carbons here. Remember, the alpha carbons are going to have the side chains. So for those of you that maybe have a handle on this, what is the one-letter code for the amino acid that has a 5-ring system with a nitrogen bonded to benzene? What is that one? The one-letter code for it. Look at this chart. Thank you, Maria. Yes, W, because that is tryptophan. So the first one, this is tryptophan. And the one-letter code is W. Let me just highlight it for those students that maybe the highlighting helps them. Next amino acid is a CH bonded to a CH3, bonded to a CH2, bonded to a CH3. What is the one-letter code for that amino acid? Look at the bonding. CH bonded to CH3, and to the other side, a CH2, followed by a CH3. No, it's not leucine, but it's cousins with leucine. Which one is it, leucine or isoleucine? Remember, a CH bonded to CH3 on one side, and to the other side, CH2, CH3. So is it leucine or isoleucine? Great. It's isoleucine. So this is isoleucine. And the one letter code for isoleucine is I. Next one. CH2 bonded to an amide. Again, the side chains. CH2 bonded to an amide. Is it asparagine or glutamine? CH2 bonded to an amide. Is it asparagine or glutamine? (50-50) on it. Great, that is asparagine. So this is asparagine. Asparagine has the one letter code N. And lastly, we have the amino acid that has 2 hydrogens connected to the alpha carbon. What is that amino acid? The one that has 2 H's. Which amino acid has 2 hydrogens connected to the alpha carbon? Thank you, Katie. Yes, that's glycine. So when it comes to glycine, the one letter code for glycine is the letter G. So this peptide spells the word wing. Okay? So on Thursday, we're going to finish the concepts of chapter 10. Okay? And that's going to be the last material for the exam. That is all for today.